Can't do your pin on it.
Boo! Welcome back, everybody. Yeah, so are we going to have a snow day tomorrow? What do you guys think?
Hopefully not.
I'd say right now it's like 50-50 shot. 50-50.
If we have a
Thursday, there's no chance Thursday. We're not getting enough snow. Like, it's going to be more rain for us. Like, up in Sandusky, they're going to get all snow. So it's like there's their chance for snow days on Wednesday and Thursday are growing a little bit. But us, if the snow holds off for longer, that's beneficial to us. It helps us. It actually helps us that, like, if you plug in Massillon zip code, that it's more snow for them than it is rain for them. And they're part of our, like, like we bus to them and everything. So, like, if they call off, we call off. All right. So this is section 4 indeterminate forms and L'Hopital's rule. Remember that for L'Hopital's rule, it only works when it is an indeterminate form, right? It only works when it is an indeterminate form. So L'Hopital's rule basically says that, in other words, when you have an indeterminate form type 0 over 0 or infinity over infinity, then you can use L'Hopital's rule. And remember that an indeterminate form is just one where, if you've got 0 divided by 0, is that 1? Is it 0? We're not really sure. Is it undefined? I don't know. Or like infinity over infinity. Like taking e to the x over x squared, like we did yesterday. E to the x is going to grow exponentially, where x squared is only going to grow quadratically. So we know e to the x is going to grow faster, but how fast is faster? Is it fast enough to cause a horizontal asymptote, basically, right? And L'Hopital's rule will tell us that. All right, and then we did a bunch of examples. Remember that we did this one, right? Did we do this one? Okay, we have not gotten to here, correct? Okay, perfect. Let's start here. Remember that I need you to state why you are using L'Hopital's rule, okay? That is important to state it. Now, can I let you in on a little secret? That's a me thing. That is a, like, the first time you're learning it, you should definitely check L'Hopital's rule before you use it. You'll notice on my homework key, if you look at the homework key, I don't check it every time, I just use it. And as you progress further along, other professors and teachers are not going to require you to show that every time. But again, it's just something that we need to check to make sure that we can use L'Hopital's rule and show that within the word. For right now, right? The first time we are learning it, it's important to check it, okay? All right, so take a look at example 4 here. We got tangent x minus x over x cubed. All right, let's see if we are going to use L'Hopital's rule. I know right away, like looking at the denominator, x to the third, if I plug in 0 there, like no good, right? I know it's going to be 0. So let's evaluate the limit as x goes to 0 of tangent x minus x. We know right now, like I can go ahead and state this. That's going to go to 0, right? If I plug in 0 there, I get 0. So let's see what happens with tangent x minus x. So that would be tangent 0 minus 0, right? What is the tangent at 0? What is the tangent at 0 degrees? 0, right? Because it'd be y over x. The y value is 0, the x value is 1. So it'd be 0 over 1. So therefore, it would be 0 minus 0 or 0. So we can say that this is the indeterminate form 0 over 0, which allows us to use L'Hopital's rule. Again, that whole process should basically go on in your head after we get through, this next quiz, this next test, I guess you should say. All right, so that means that I can take the derivative of the numerator separately from the derivative of the denominator. Oh, that's not full. I can take the derivative of the numerator separately from the derivative of the denominator. And again, let me note that you are not using quotient rule here, right? You are not using quotient rule. You are using them separately. So, did anybody remember the derivative of tangent? It's secant squared? Negative secant squared? Tangent, just positive secant squared. Positive secant squared. So secant squared x Minus 1 is the numerator, right? And then the denominator is 3x squared. Okay, let's plug in 0 again. Right? Let's plug in 0 again because this is the limit as x goes to 0 of this thing. Well, again, what's going to happen to the denominator? It's going to go to 0 again, right? It's going to go to 0 again. So my guess is this is going to be another indeterminate form. We're going to have to do L'Hopital's rule again. But let's check. Let's say, and I'll kind of write it off to the side so we don't use too much room here. The limit as x goes to 0 of secant squared x minus 1. Okay, secant squared, that's 1 over what? 1 over cosine, right? 1 over cosine. I don't need my calculator here. 1 over cosine. Well, what's the cosine at 0? What's the cosine? 1, right? The x value is 1 at 0. So this is going to be 1 squared, which is 1, minus 1, which is 0. Okay, yeah, that makes sense then. This is going to be of the indeterminate form. 3x squared. I shouldn't talk while I do math. 0. This is going to be the indeterminate form 0 over 0. Right, this is going to be a 0 over 0 form. Okay, well now we have to find the derivative of the numerator separately from the denominator. Okay, so we can say that this is going to be the limit as x goes to 0 of, okay, what's the derivative of secant squared? Ooh, what's the derivative of secant? That's a weird one. Secant x tangent x, right? Secant x tangent x. But the weird thing is, isn't secant squared like this, right? What do we have to use? The chain rule. Yeah, so this is actually going to be 2 secant x times the derivative of secant, right? Times the derivative of the inside, which the derivative of secant, just reading off our formula sheet here, secant x tangent x. Now, the nice thing about that is what's happening to the minus 1. Right? So now we have on the bottom a 6x. All right. Okay. We can reduce that down a little bit. So this is limit as x goes to 0 of 2 secant squared x tangent x. Divided by 6x. Sorry, I forgot my denominator there. I think we're chasing down a rabbit hole a little bit. What's going to happen to the denominator again? It's going to go to 0 again. Now, you know what the nice thing about this is? The next iteration of L'Hopital's rule, isn't the x going to go away? So like I know the next one, it's like there's light at the end of the tunnel. I know the next one it's going to stop, but I'm guessing this is going to be another indeterminate form. Let's find the limit of the top. The limit as x goes to 0 of 2 secant squared, that's an e, 2 secant squared x tangent x divided, oh, no, sorry, just the top. What's that going to come out to be? Oh, actually, I lied. That's not 0, is it? What was secant squared of 0? 1, not 0, but 1, right? Ooh, this is interesting. So this is going to be 2 times 1 times, well, what's the tangent at 0? Oh yeah, this is going to be 0, isn't it? Well, that's quite a bummer. That's quite a bummer. I thought it was. I thought we were going to be able to get around it. Oh, they can't. I get it. Keep it. Yeah, just forget about the 0. No, just can't. We can't do The limit as x goes to 0 of 6x is also going to be 0. So therefore, this is the indeterminate form 0 over 0. Okay. One more time. Now, the derivative of the numerator is going to be weird, right? We're going to have to be very careful with the derivative of the numerator. We can do it, though. The nice thing is, what's going to be the derivative of the denominator? 6, right? Okay. Now, the derivative of the numerator, I've got a couple weird things happening, right? I've got 2 times the product rule, right? 2 times the product rule. And again, our product rule is fg prime plus gf prime. Okay, f is secant squared x. The derivative of tangent, secant squared x. Plus and then looks like the derivative, what do we have to do again? What's the derivative of, sorry, I guess I should put tangent first. Tangent x times the derivative of secant squared. Did we just do that? What was the derivative of secant squared? It was 2 secant x times secant tangent x, right? It was this whole chunk. Right? We just did that. 2 secant x, which takes care of the chain rule, times the derivative of secant, which is secant tangent x. So all said and done, it was this thing. Just going to copy, paste. So I'm going to need a little bit more room, though. Let me move that. Where are you going? Move this down a little bit. What are you doing? Just want to move you down. Times 2 secant squared x tangent x. Okay. And we are going to find that, the limit, as x goes to 0. Okay. What's going to happen secant of 0? 1, right? So this is going to be 1 times 1. So all of a sudden, this is 2 times 1 plus. Okay. What's the derivative? What's the derivative? What's tangent 0? 0. So what's happening on this whole chunk? That's all going to go to 0, right? Okay, we can do that. That's just 1/3. Done. Whoa. So you can kind of go down a rabbit hole of using L'Hopital's rule as many times as you may need, right? 2, 3 times if you need to. The issue is, the more you take the derivative, the weirder things may get. Yeah. If it's polynomial, things are going to reduce. If it's trigonometric, things are just going to get weirder and weirder and weirder. You just have to. It just varies by type of function that you have. Do I want to do this one? Oh, I want to talk about this one. You don't necessarily have to write this one down, but I do want to talk about this one. Okay? Because let me just say this. If I didn't force you into checking L'Hopital's rule, you might try to use it, right? But watch. The limit as x goes to pi from the negative side of sine is going to be what? What's sine of pi? What's the y value at 180? 0, right? Okay. So I have 0. And then the limit as x goes to pi from the left side of 1 minus cosine x. Well, what's the cosine at 180? See, and this is where you might get tripped up and say, oh, it's 1, so it's going to be 0 as well, because your mind wants to go there, right? Your mind wants to use L'Hopital's rule. Your mind's just going to go there, right? What is the cosine at 180? -1. Oh, that's 2, not 0. Is this L'Hopital's rule? No. The limit as x goes to pi from the left is 0 over 2. I'm sorry, of this thing is 0 over 2, which is not an indeterminate form. That's just 0. 0 divided by 2 is 0. Right? So that's why I want you to keep checking using the hypothesis of L'Hopital's rule, the fact that it has to be an indeterminate form. Okay. All right, so we've studied the indeterminate forms of 0 over 0 and infinity over infinity, right? And those are the types that need L'Hopital's rule. There are other types of indeterminate forms, okay? There are other types of indeterminate forms. There are indeterminate forms of the type 0 times infinity, right? 0 times infinity. They explain this one really silly. They say, okay, they got two functions, f and g, right? You got two functions, f and g. What happens if the limit of the first function is 0 and the limit of the second function is infinity? Is it going to be 0? Is it going to be infinity? Which one's going to win out, right? Which one goes fat first? Does the first function go to 0 first, or does the second function win out and turn it into infinity first before it gets small enough that it goes to 0? See, which one wins? F or G? Does it go to 0? Does it go infinity? We don't know. That's an indeterminate form. There's another type of indeterminate form. However, L'Hopital's rule doesn't apply because it's not a rational function. It's not one over the other. However, we can make that happen. We can make that happen. If you have an indeterminate form of the type 0 times infinity, where one of them is 0 and one of them is infinity, what you can do is say, well, if I can make the infinity one 1 over infinity, what does it turn into? What does 1 over infinity turn into? 0. Thus turning it into a 0 over 0 indeterminate form, which I can then use L'Hopital's rule. So what I do here is I take the one that goes to infinity and I make it the reciprocal, right? By dividing by the reciprocal, right? Notice that I'm not changing anything when I divide by the reciprocal, right? I divide by 1 over the reciprocal, and that's the same thing as just multiplying by it, right? I'm just changing what it looks like a little bit so that I can force L'Hopital's rule into working, right? I can force L'Hopital's rule into applying, right? So it's kind of like a trick, right? It's kind of like a unique, very specific way of solving these problems. When you have an indeterminate form of the type 0 times infinity or infinity times 0, you take the infinity and you turn it into a 1 over that thing, right? You divide by the 1 over, you divide by the reciprocal of that value, and that will turn it into an indeterminate form type 0 over 0. Or it might turn it into an infinity over infinity if you flip the other one. And then you can use L'Hopital's rule. Okay. Let me show you how that works. X ln x. Seems really simple, right? Indeterminate form of the type x, or sorry, if I plug in, right? If I plug in, let's see what's going to happen. The limit as x goes to 0, and I have to say on the right, and you'll see why here in a second, of x, well, if I plug in there, I get 0, right? All right, so what's going to happen to ln? The limit as x goes to 0 from the right of ln of x. Think about the graph of the natural log of x. If I look at the graph of the natural log of x, it's going to look like this, right? What's the limit on the right side of 0 of the natural log? Negative infinity. We know by graphically that the closer I get to 0, the smaller and smaller I plug in my values into the natural log, the more negative I get. So this is the indeterminate form type 0 times negative infinity. See, we state in this case, what's going to go faster to its value? Is just the function y equals x going to go faster to 0? Or is it going to go faster to 0 on the natural log? Which one's going to win out? That's why it's an indeterminate form. We don't know. So here's what we can do. We can take, now in this case, I am going to turn, I know I said to use the infinity one, so I would be using ln of x. It's actually easier to use x by taking the reciprocal of x, because the reciprocal of x is just 1 over x. So I'm going to take ln of x divided by 1 over x. You divide by the reciprocal of one of the functions, and that will turn it into an indeterminate form. Watch and see. We're still finding the limit as x approaches 0 from the right. Right? Okay, look at this. The limit as x approaches 0 from the right of ln of x was I could go straight to finding the derivative now. I'm sorry. I don't need to check this. Once I determine it's an indeterminate form. I'm sorry. Go back. We go limit as, I didn't need to erase all that. Ln of x over 1 over x. Sorry. Once you determine it's an indeterminate form, you can go straight to using L'Hopital's rule. Sorry. So now I can say, well, what's the derivative of ln of x? 1 over x. Right? That's the derivative of ln. Now, in other words, like the denominator here, isn't that just x to the negative 1? So be careful when you take the derivative there. That's just going to turn into negative 1 x to the negative second. Okay, well, 1 over x was just x to the negative 1. So I've got x to the negative 1 over negative 1x to the negative second. And my algebra students would tell you that you subtract those exponents, right? So this would be negative x to the negative third, right? Oh, sorry. No, that's a lie. My algebra students would say, no, that's not right, Mr. Laverick, because you got to do minus the negative. Negative 1 minus negative 2, that's a plus 2. Right? So just negative x. So now I evaluate the limit. The limit as x goes to 0 from the positive of negative x is just 0. Questions about that? So sometimes you can use the indeterminate form 0 times infinity, or infinity times 0, 0 times negative infinity, like we did in this case, and use L'Hopital's rule for it. There's another type of indeterminate form. There's actually a lot of types of indeterminate forms. There's only one other one that we're going to look at, though. It's the type infinity minus infinity. Infinity minus infinity. So that's just one other type of indeterminate form. Now, L'Hopital's rule in this case, it only applies to rational functions. This is just more like, does a indeterminate form exist in certain cases? Like there are problems in your homework where you have to decide is it an indeterminate form or not? And this is just another indeterminate form that you would have to decide with. You can't really use L'Hopital's rule on this unless you get really fancy with it, and I won't be asking you something like that. Okay. If you print out the notes, we're going to stop there. Just know that they're for you guys, just for fun. There are many other types of indeterminate forms. I will not be asking you about indeterminate powers like this, but there are other types of indeterminate forms, like 0 to the 0 power. Is it 1? Because that's a rule for the 0 power. But is it, if it's 0 to the 0, is it 0 or is it 1? We don't know. The type infinity to the 0 or 1 to the infinity, all indeterminate form types. All right, I will let you work on your assignment. If you had, oops, sorry, let me stop the video.